In this discussion, we are going to learn how to solve a system of equations of ODEs by the matrix method. So in that, we're going to learn how to use eigenvectors to solve a system of ODE. So let's start with the normal form. A normal form of a first order system. Normal form of a first order system of linear equations. First order system of linear equations. First order system of linear equations is, you can write in this form. So it is a x1 prime, which is a function of, so you have some constant, I'm going to call it a11, that's the first constant, which is a function of t times x1 plus another constant, I'm going to call it a12t. Actually, it's not a constant, it's the coefficient, but it is a function of t. And then x2, like that. And then we have a1n, the coefficient function, actually the coefficient function of xn, plus then we have a function of t. So that's the first equation. And then the second equation, we can write like this, x2 prime a21. So the first number is a row number, second one is a column number, which is a function of t, x1 plus a22 t x2, like that. And then we have a 2n t, which is a function of t again, xn plus f2t. So like that we can continue this pattern. Then we have x n prime, which is equals to a n1 t x1 plus a n2 t x2, like that. And then a n t xn plus fn t. So you can see that there are so a lot of equations here. There are actually n equations here. So this is what we call the normal form of a system. So you can see how it works. You can see there are n many dependent solutions. So those are x1, x2, xn. Those are the solutions. And then we have the first derivatives here. So this is how you write the system. This is what we call the normal form of the system. And then if, so the special case, if fi t equal to 0 for all I going from 1 to all the way up to n, we call the system is a homogeneous system. So the system is said to be homogeneous. And otherwise, so that means if there's at least one ft function which is not equal to 0, we call the system is non-homogeneous. So otherwise it is non-homogeneous. Good. So it is homogeneous if all the constant functions, all the fi functions are 0, and then if at least one is non-zero, we call it a non-homogeneous system. In this, actually, we in this discussion we only going to focus on the homogeneous system. That means those ft functions are 0. Those are the ones we're going to try to solve. So now let's try to introduce the matrix notation. So the matrix form of a system matrix form of a system. So you're going to define a vector. So let x, a, and f, these are all function of t, be given by, so let's say x. So this is a vector. So the component, we're going to pick those dependent functions. So x1, that's the first component, which is a function of t, and x2, that's the second component, like that. And then we have xn, that's the third nth component. So this is, we're going to put those as components, and we create this new vector. So we're going to call it, this is a vector which has one column and n many rows. So this is a vector. It's a column vector. So we're going to call this a column vector, or simply a vector. Okay, we just say vector. When you say vector, we normally mean a column vector. And then so similarly, we can define the coefficient matrix that we call AT. So we're going to pick all those small a functions. So that means A11T, and then A12T. So the first number is the row number, second one is the column number, like that. So we have A1NT. So similarly, we can go A21T, A22T, like that, A2NT, and then so we can keep going like that. So it is AN1T, and then A, so we just put a little space between AN2T, like that, and we have ANNT. So there are n squared many numbers. There are n many rows and n many columns. We call n by n matrix, which is a function of t. You can see that this is a function of t, but we mostly deal with the case where those functions are constants. That's what we're gonna focus on, constant function. And then we have the ft. We have ft, which is simply we have f1t, that's the first component, f2t, the second component, like that, fnt, that's the nth component. So that's what we have. So this is a n by 1 matrix. It's also n by 1 matrix. Why? There are n many rows, only one column. Good. Now what we can do, using this one, we can write the system. So actually what I'm going to do, I'm going to remove this part from here, then I can write that there. So we, using this notation, we can write the normal form in the so this is a vector, so like that. So vector. The second one is a matrix. This is a matrix, and this one is again a vector. Good. Now what we can do is we can write the system can be written as, okay, so then the system that we had at the beginning, then the system can be written as like that. So we can say the derivative of the x function, so that's the function, we can say x1, just ignore t for the moment. Okay, so that's still a function, we can take the derivative of that. So what we mean by that, we're going to take the derivative component wise. That means we can take the derivative of x1, derivative of x2, derivative of xn. So we can write it like that. And then we can write the x, like we had the constant times x functions. So those we can write as a matrix product. So what's going to happen, we can write that as a matrix vector product. So we only write the coefficient here. These are functions of t. So like that, we only write the coefficients here, a1n, and then a21, a22, like that, a2n, and then we have an1, an2, n n, like that. And then so we can write this as a matrix product, so we just put the coefficient and then we write the x as a column vector. So it is x1, x2, xn. So this is what we discussed in linear algebra. So we can write this as a matrix vector product. So this is a matrix vector product. Plus, then what's going to happen? We have that f1 functions, f1t, and then f2t, like that, fnt function. So that's the non-homogeneous part. So now what's going to happen? You can see that what we have here, this is simply the derivative of the x function. So this we're going to call the a function, or at. We just say a, but it's a function of t. But it can be constant. That's okay. And this is again x vector, and this is we're going to call the f vector. So we can use uppercase letters for that. You can put the t there. Sometimes we even ignore that t, but it is like understood. So this is what we can do. So now what we can do, we can write this whole system simply as a vector equation. So we can write this system like this. So so in matrix notation, so in matrix notation, so we can write the system as x prime equal ax plus f. So this is what we call the matrix form of the system. So I'm going to call this equation number 2. So this is a matrix form of the system. Now, sometimes what happens is f function can be all 0. So if this is the case, so we can say if the system is homogeneous, if the system is homogeneous, that is f function is 0, we can write this one as x prime equal ax. So this is number 3. So let's look at a few examples on how to put a system in this form. So let's look at some examples. So we can say write as a matrix equation. Okay? Matrix equation. So let's start with A. So let's say we have dx over dt, which is equals to 3x plus 4y, and then we have dy over dt, which is equals to 5x minus 7y. Now what we can do, so say let x, we can define the x vector, which is simply x and y. The two solutions, we're going to put it there, x and y. So then what happened? Then, so I'm going to write it here. This is easy. So then x prime is simply x prime y prime vector. So we're going to put x prime y prime as the component. So then what you can do is you can simply write this whole system as x prime equal to, just pick the coefficient, 3, 4, 5, negative 7 times x. So this is the matrix version of the system. Very easy. Let's look at a larger system. So how about this one? B. So you can write as dx over dt equal 6x plus y plus z plus t, and then dy over dt equal 8x plus 7y minus z plus e to the t, and then dz over dt, let's say 2x plus 9y minus z minus ln t. So the same thing, let x Now this vector has three components. We have x component, y component, and the z component. So then what happened? As before, x prime is simply x prime, y prime, z prime. So then we can write the system. We have x prime, which is equals to, that's that vector, which is equal to, let's put the coefficients there, 6, 1, 1, 8, 7, negative 1, 2, 9, negative 1 times x. So we can write it like that. Plus, you can see we have these extra non-homogeneous functions. So what we can do, we can write this as another vector. So these are the components. The first component is t, the second component is e to the t, third component is minus ln t. So we can write this as a extra vector. Good. So that is the system in the matrix form. So what we did, we just put the, so this is the A matrix, which is a 3 by 3 matrix, which has only the constants. Now let's define few other terms. So what we mean by a solution vector? So the definition, solution vector, vector. So what's solution vector? A solution vector on an interval I is any column vector is any column vector is any column vector is any column vector x which has components, let's write that later, which has components x1t, x2t, like that, xnt if they have many components. So that's the column vector that satisfies either equation 2 or in the homogeneous case equation 3. So if we have a vector that satisfies the equation 2, that means x prime equal ax plus f, that's the equation 2, then we call it is a solution vector. So what we can do, we can take the component wise derivative, and we have the A matrix, and then we have X matrix, and once you plug in, it should satisfy the equation. So it's exactly the same thing as we did with ODEs, but what we do now, we have n equations, so that's the only problem here. Okay, and then also let's talk about what we mean by linear independence. It's also very similar. So linear independence. So you can see it's also very similar. So let we can say x1, x2, and xn be a set of solutions, set of solution vectors, set of solution vectors of the homogeneous equation, solution vectors of the homogeneous equation, set of solution of the homogeneous equation x prime equal ax. So let's say on interval I. Then the set is linearly independent. The set is linearly independent. The set is linearly independent. Very similar argument, very similar expressions. Independent if C1 x1 plus C2 x2 plus like that Cn xn equals 0, 0 implies that C1 equals C2 equal like that Cn equals 0. Otherwise, so it doesn't imply, that means what it doesn't imply means, that means there are some non-zero C's that still make the equation 0. This otherwise means, otherwise the set is linearly dependent. Otherwise the set is linearly dependent. Okay, so we also have a similar Wronskian test for that. So let's look at the Wronskian test. So we have the Wronskian test. So we can have the Wronskian like this. So it's W. So we have the solutions, which is x1, comma x2 like that. So let's say we have n many solutions, so xn. So what we're going to do, we're going to create the determinant where x1, we're going to put the component of x1 as the column. So x11, x21 like that. This is n1. So this is the x1 vector. So we put the vector like that, just as the column, and do the same thing. We put the second vector here. So 2 1, 2 2. Actually the other way. So this is 1 2, and then like that. So this is x n2. So that's the second vector. So we're going to put those vectors as columns. And then the last one is 1n, that's the nth vector, 2n like that, is xnn. So that's the nth vector. This is xn. So what we can do, we can check whether this determinant not equal to 0 for some, not all, for some t naught in the interval I, the same interval. So we only need, as before, just one number that doesn't make this not equal to 0. So we just look at the determinant, and you can see that there are no derivatives at this time. There are no derivatives. So this is very easy to do. How we normally do is we're going to check whether each column has a pivot. Okay, that's what we normally do. So so check each column. Check each column. Has a pivot. So look at the other video about the linear algebra basics for differential equations. There I explain those basic results. So what we normally do is we check whether each column has a pivot element. That's how we check. Then it is not equal to 0, because it's going to be linearly independent. In other words, the determinant not equal to 0. That's the connection between the two. Okay. So, and also you can see that there are no derivatives. So that's the other one, no derivatives. So that's the other difference. Because in the regular case, we need derivatives, but here we do not have derivatives. Okay, so let's write the general result. So how to write the general solution? It's also very similar to the, we have this general theorem. So what it says that, so this is general solution of a system of ODEs. So it is very similar to the regular ODE case. So let's say let x1, x2, and then xn be a set of linearly independent. It's very important. Linearly independent. linearly independent solutions. Independent solutions of the homogeneous system, homogeneous system x prime equal ax. So we're going to find n linearly independent solutions of the homogeneous system on an interval I. Then the general solution of the system on same I is, we can write exact like we did before, C1 x1 plus C2 x2 plus like that Cn xn. So what we do, we're going to consider the linear combination of the solution vectors. So we're going to find n linearly independent solution and write the linear combination. That's going to be a general solution where Ci are constants. So that's the general solution. You can see that this is very similar to the regular case. And also, in addition, if xp, remember the particular solution, so it's the same thing. If xp is a particular solution, of the non-homogeneous system x prime equal ax plus f, the general solution is very similar. X equal again C1 x1 C2 x2 like that, and then we have Cn xn plus xp. So and this is the complementary solution as before. So we know that it is simply x, what we normally do is xc plus xp. That's the same thing, so it even works for the system. So this is just a general theory. So every time I tell you the same thing, simply extended for systems. So now let's talk about what we have been waiting for, the eigenvector method. So let's talk about eigenvector method to solve a system of ODE. So let's talk about that now. So the eigenvector method, eigenvectors method. So eigenvectors method. So before we talk about eigenvectors method, we want to talk about what we mean by eigenvalues and eigenvectors. So let's write that first. So eigenvalues and eigenvectors. Eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So let's say let A be an n by n matrix, lambda is called an eigenvector, eigenvalue. Lambda is called an eigenvalue. It's one word. Eigenvalue. Lambda is called an eigenvalue of A if there is a non-zero vector nu, if there is a non-zero vector. It's very important because zero case is not really important. Non-zero vector, if there is a non-zero vector nu such that non-zero vector nu such that like a nu equal lambda nu. So if you can find a non-zero vector such that when you multiply a with nu, you exactly get lambda nu. Because what will happen when you multiply a vector with a matrix, what's going to happen? It's going to rotate the vector. So what this theorem says that the rotation is simply become a translation, because when you multiply by a lambda, it's going to scale it. So what happened? What this says that the rotation is exactly equal to a translation. So if that is the case, then we call it a eigenvector, and the value is called the eigenvalue. So so this is like a very strange situation, because you start with a vector, you're gonna operate on a matrix, so it's gonna rotate it, but the rotation is simply become a scaling. If that is the case, we call that lambda is the eigenvalue and nu is the eigenvector. Good. Yeah, so that's the geometry representation of that. So the v actually this is the nu. The nu is called the associated eigenvector of lambda. For each lambda, there is associated eigenvector. So the nu is called the associated eigenvector of lambda. The associated eigenvector of lambda. Now let's see. So those are the definitions. So that means if you are given a matrix, if you can find a lambda and a nu such that a v equal lambda nu, a nu equal lambda nu, you call lambda is the eigenvalue, nu is the eigenvector. Now what we can do, we can see a little bit more rewriting. So what we can do, we can bring this to one side. So we can write this one as a nu minus lambda nu equals 0. Is a 0 vector now, and we can factor out nu. So how to factor out nu? Minus, you cannot just pick lambda out because a is a matrix. Lambda is just a number, so you cannot subtract a matrix from you cannot subtract a number from a matrix. It has to be another matrix. So what we normally do is we're going to multiply by the identity matrix. So that now they are both matrices, so you can subtract them. So that's how we normally write, and then nu equals 0. So, but we know that we are interested in finding a non-zero v. But we know that in linear algebra, theory of linear algebra, if the matrix A minus lambda is what we call invertible, if it is invertible, that means there's inverse, then the only solution this has is nu equals 0. That is not interesting because we know that that's not eigenvalue. So that means A minus lambda I cannot be an invertible matrix. It has to be what we call non-invertible, in other words, singular matrix. That means if it is a singular matrix, we know that the determinant is 0. So that is the condition to find the eigenvalues and eigenvectors. So the determinant of that matrix has to be 0 so that that matrix is non-singular. That means there's no inverse. So that means columns are linearly dependent, not independent but dependent. Okay, so let's talk about that. For non-zero solution, okay, for a non-zero solution, for a non-zero solution, A minus lambda I, the matrix, should be singular. Should be singular. So that means, in other words, So then what happened? Singular means the determinant of that matrix has to be 0. So that is the condition to find the eigenvalues and the eigenvectors. So that's the condition. And this equation is what we call the characteristic equation. So we call this equation the characteristic equation. This is called the characteristic equation. This is called the characteristic equation. And the solutions, this equation has solutions because you can see that there is a polynomial of lambda. So that polynomial has solutions. Polynomial equation has solutions. This is called the characteristic equation. It's called the characteristic equation. And the solutions of that equation, are called eigenvalues. The solutions are called eigenvalues. So now the next thing is, let's try to find few of the eigenvalues. And then also we can actually, we have just few more. The non-zero solutions. The non-zero solutions of A minus lambda I V I nu equals 0, because this is just like a Ax equals 0 situation. So there may be some non-zero solutions, or what we normally call the null space. We try to find the null space. The non-zero solutions. 0 is always a solution. That's useless. So the non-zero solutions are the corresponding eigenvectors. And then actually we discuss in another video, we discuss a shortcut method to avoid this path, because this can be really lengthy. Normally when you try to do that, it needs like 6 steps. So we can write the A minus lambda matrix, and then we're going to simplify it, and then row reduce, write the corresponding system, and then write basic variables in terms of free variables, and then write the parametric vector form, and then we find the eigenvector. So that's the kind of lengthy, very lengthy process. So you have like 6 steps. But rather than doing this, we discuss a shortcut method. So we can use a shortcut method to find the solutions for this one, because it's much easier. And then let's write this very important theorem. So this is the main theorem of this method. So the theorem. So what it says that, so consider the homogeneous system. Consider the homogeneous system x prime equal ax. So we have this what we call system matrix. So we have matrix. So we can write x prime equal ax. And then let lambda 1, lambda 2, like that, lambda n be real eigenvalues. And then not necessarily distinct. So they may be the same, okay, not necessarily distinct. And if there are n linearly independent eigenvectors, if there are n linearly independent independent eigenvectors, if there are n linear independent eigenvectors corresponding to the eigenvalues, eigenvectors corresponding to the eigenvalues lambda I, the general solution, I'm going to call this star, the general solution of star is given by like this, x, which is equal to Ci, the corresponding eigenvector v1 e to the lambda 1 t. So that's the form, very simple. C2, put the eigenvector e lambda 2 t, like that, and then we have Cn Vn e to the lambda n t. So that is the formula. Very simple. What we need is the eigenvalue and the eigenvector. We write this as a solution, where Vi is the associated eigenvector of lambda I, is the eigenvector of lambda I, because we know that for each lambda I there is associated eigenvector. If those eigenvectors are linearly independent, that's the interesting part, it has to be linearly independent. If those eigenvectors are linearly independent, then this is the general solution. And we also say that they may not be distinct, it can be even equal, but the only thing is that the eigenvectors has to be linearly independent. If that is the case, then we can write the general solution in this form. So this is the general solution. Very simple. So we only need to find eigenvectors and the eigenvalues, and if you know that, just plug in there, get the solution. So let's look at like now several examples, and before that I want to give you like a one interesting fact. So that's a theorem. It says that eigenvectors corresponding to distinct eigenvalues are linearly independent. So eigenvectors corresponding to distinct eigenvalues are linearly independent. That's the result. This is one of the like a very beautiful proof, but we are not going to prove that here. So but this says that eigenvectors corresponding to distinct eigenvalues are linearly independent. So that means if you know that the eigenvalues are all distinct, corresponding eigenvectors are automatically linearly independent. Okay, so let's start with the 2 by 2 matrix first. So example 1, solve this system. So dx over dt equal to x plus 3y, dy over dt equals to 2x plus y. So then what we can do is, so we write here, so let x equal x and y, those are two solutions. So then what we can do, we can write this system as x prime equal the coefficients 2, 3, 2, 1, those are the coefficient times x, so we can write it like that. So now the steps are, we're going to find eigenvalues first. So the first step, find eigenvalues. To do that, we're going to look at the determinant of a minus lambda I, a minus lambda I. So that means we can subtract the we can subtract lambda from the diagonal entry. So it is 2 minus lambda, 3, 2, 1 minus lambda. But those are diagonal entries, and we can expand this. Once we expand this, you're going to get 2 minus lambda. So it's a 2 by 2 matrix. If you have 2 by 2, we're going to multiply this and subtract that. That's how you find the 2 by 2 determinant. So you're going to get that, and 1 minus lambda minus 6. You set this equal to 0. And you can see that this is very easy to find factors. So this is lambda squared, and you're going to get negative 2 lambda, negative 3 lambda. So we have negative 3 lambda, and then we have 2 minus 4, that means 4. And then you can see that this is easy to factor. So it is lambda minus 4, lambda plus 1 equals 0. So this says that, so the eigenvalues are lambda equal negative 1 and 4. So those are the eigenvalues. Now what we're going to do, we're going to find the corresponding eigenvectors. So we can use the shortcut method for that. So the step 2, find the eigenvectors. Find eigenvectors. So we can use the shortcut. But the shortcut says the column of the eigenmatrix are the eigenvectors, and that's it. How to get the eigenmatrix? Just subtract the eigenvalue, the other eigenvalue. So let's write the result. So the result, what it says that so eigenvectors. So let's say for a 2 by 2 matrix, it doesn't work for a large matrix. It works for when you have 2 eigenvalues. For a 2 by 2 matrix, eigenvectors are the columns of are the non-zero columns. The non-zero columns of the complementary other complementary eigenmatrix. That's a new word that I introduced to mathematics. So you can find that information in the other video that is solely for the finding eigenvectors. But that's the same thing. So it says that for a 2 by 2 matrix, the eigenvectors are simply the non-zero columns of the complementary eigenmatrix. Complementary means use the other eigenvalue. So let's use that fact now. So that means for lambda equal negative 1, what we're going to do, we're going to look at the eigenmatrix. We use the kappa for that. So kappa, the other one, that means 4a. So that means this is simply a minus 4i. So that means subtract 4 from the diagonal entry. So that means 2 minus 4, 3, 2, 1 minus 4. So which is simply equals to negative 2, 2, and 3, negative 3. If you want, we can scale it. So if you scale it, for example, just pick any column. You can see they are just the multiple of each other because those are eigenvectors. So I'm going to pick first column and then multiply by negative 2. That means the eigenvector for lambda equal negative 1 is simply 1 minus 1. Because you can scale it by just divide by any number so that you have something like simple. So you can divide the first one by negative 1 or the second one by 3. So you get that one. So that is the eigenvector. Or you can just pick these ones as it is, or just divide and find simple. So that's the eigenvector for lambda equal negative 1. So we do the same thing for lambda equal 4. Now for lambda equal 4, we can look at the kappa matrices for -1. So that means you subtract -1. So subtract means you add 1. So 1 plus I. So that means you simply add 1 to the diagonal entry. So you're going to get 2 plus 1, 3, and then 2, and then we have 1 plus 1. This is simply 3, 2, 3, 2. They are the same. You don't want to scale anything here. So that means the eigenvector for lambda equal 4 is simply 3, 2. So those are the eigenvectors. Now what we can do, we can write the solution. It's very simple. So let's write the solution. Therefore, the general solution of the system general solution of the system is X, which is C1, the eigenvector E lambda 1t, plus C2, the eigenvector E lambda 2t. Because there are only two eigenvectors, they are eigenvalues, they are distinct, so these solutions are automatically linearly independent. So everything looks good. So that means it is C1, first eigenvector is this, times e to the negative t, plus C2, the second eigenvector is 3, 2, e to the 4t. So that's the solution where C1 and C2 are constants. Good. So let's look at another example, like 3 by 3 example with distinct eigenvalues. So let's look at the distinct eigenvalues. Distinct eigenvalues. So let's say solve the system. Let's say x prime equal negative 4x plus y plus z, y prime equal x plus 5y minus z, c prime equal y minus 3z. So then you can write this system using matrix notation. So we can say x prime, which is simply x prime, y prime, z prime, equal, write the coefficients, which is negative 4, 1, 1, 1, 5, negative 1, 0, 1, negative 3 times x. So that is the matrix A. As before, we're going to first find the eigenvalues. So let's do that. For eigenvalues, the determinant of A minus lambda I equal, we're going to subtract the lambda from the diagonal entry, negative 4 minus lambda 1, 1, and then 1, 5 minus lambda negative 1, and then 0, 1, negative 3 minus lambda. So we're going to set this equal to 0. That's the characteristic equation. We can expand. So you can expand this along any row or column. So we're going to pick the first column because which has some zeros there. So we can do that. So if you do that, you're going to get negative 4, negative lambda times the determinant, the minor. So minor is 5 minus lambda, 1 minus 1, 1 negative 3 negative lambda. So the sign convention, which is plus and a minus and a plus. So this next number is minus. The number is 1 times, we can delete the row and the column. We can delete the row and the column that has that number. So that means we can delete the first column and the second row. So you're going to get 1, 1, 1, negative 3, negative lambda. Okay, so this is not that bad. So if you expand, you get negative lambda plus 4 here, and if you multiply through, you're going to get lambda squared, and then we have negative 5 lambda, negative positive 3 lambda, you get negative 2 lambda, and then we have 5 minus 5 times negative 3 is negative 15, and then negative, negative, positive, so we have 1, negative 1, because we need to multiply this and subtract that. So that means you're going to get negative 15 and then also plus 1, so that means you're going to get negative 14. So that's what you get when you simplify the first determinant minus. From the second determinant, you're going to multiply the first one and subtract 1. That means it's going to be negative 4, negative lambda. Now you can see lambda plus 4 is common, so you can take it out. Lambda plus 4. So you're going to get, so if you take lambda plus 4, you're going to get lambda squared minus 2 lambda minus 15. And then you can see that this is very easy to find factors. So the factors are lambda plus 4, lambda plus 3, lambda minus 5. You set this equal to 0, you get the zeros. So there are 3 zeros. So the eigenvalues are lambda equal negative 4, negative 3, and 5. And they are all distinct. Since they are all distinct, the corresponding eigenvectors are linearly independent. Okay. So these are. So we can say since they are distinct, the corresponding eigenvectors are linearly independent. Okay, so that's a fact. So what we need to do is just need to find the corresponding eigenvectors. That's not that bad. That's easy to find. So let's do that. So what we can do, we can look at the eigenmatrices. So consider 3 eigenmatrices. Consider the 3 eigenmatrices. So we're going to go with the first eigenvalue, negative 3a. That means you're going to add 3 to the diagonal entry. So that means this is negative 1, 1, 0, 1, 8, 1, 1, negative 1, 0. That's the first one. The second one is kappa, negative 4a, which is 0, 1, 0, 1, 1, 1, 1, negative 1, 1. And then the next one is kappa 5a, which is 1, 1, 0, 1, 0, 1, 1, negative 1, 2. That's the third one. So from the theory, we know that the to get an eigenvector, what we're going to do, we're going to multiply the other 2 matrices. To get an eigenvalue of negative 3, you multiply the other 2 matrices. But you don't want to multiply the whole matrix. We only need to multiply one column of one matrix with the other one. So what we normally do, we're going to pick one with many zeros just to make the calculation easier. So for example, for lambda equal negative 3, for lambda equal negative 3, what we can do, we're going to multiply the kappa matrix of 5 with the with this column, because there's so many zeros. So we're going to multiply that. So we're going to pick the other two matrix. You multiply one matrix with just one column of the other. So so that means we're going to multiply that. So 0, 1, 0. And if you multiply by that, and you can see that I'm going to write this one. This is the first example. 1, 1, 0, 1, 0, 1, 1, negative 2, no, 1, negative 1, 2 times 0, 1, 0. So what does that mean is, just pick, this says that when you multiply, because since you only have 1 in the middle, you only pick the entries in the second column. So you pretty much, you're going to pick this column. So that's the answer. That's a kind of shortcut. So you're going to get 1, 0, 1. So, and you can see that this is not equal to 0. That means that's the eigenvector. So that means the eigenvector of negative 3 is 1, 0, 1. You can scale, but here you don't want to scale. It's like good number. And then do the same thing. So for lambda equal negative 4, again negative 4. So we can go with similar arguments. So I'm going to say kappa matrix of 5 with, I'm going to pick just one column of the first matrix. So just pick something. So if the product is not equal to 0, you good. So I picked the third column, because that has some kind of zeros there. So if you multiply by that, what do you get? So again the same argument, 1, 1, 0, 1, 0, 1, 1, negative 1, 2, and this is not that as good as quick as last time. So when you multiply, what do you get? So you can see that when you multiply this, how you multiply, you pick the first row and multiply the corresponding entries and add them. So that means you're going to get 1 plus 1, 1 times minus 1, so minus 1, when you add them 0, so you get 0. And multiply the second column. When you multiply the second column, you're going to get 1 times 1 and then 0, 0, so you get 1. Multiply the third column, so you get 0, negative 1, so you get negative 1. So this is what you get. This is good enough. So if you want, you can multiply by negative 1, but you know, this is good. So lambda equal negative, so eigenvalue for negative 4 is simply 0, 1, negative 1. And then for the last one, so you can see for lambda equal 5, for lambda equal 5, so the kappa matrices of negative 3a is, so what we're going to do, we're going to, no, so what we are doing is we need the eigenvector for lambda equal 5. So this is for lambda equal 3, this is for lambda equal negative 4, this is for lambda equal 5. So that means lambda equal 5, you're going to pick the other two matrices. So just pick one matrix and multiply by the other one. Since the kappa matrix for negative 4 has 0, 1, 0, I'm going to pick that same one. So I multiply the first matrix by that. So this means that pick the second column. That's what it means. So negative 1, 1, 0, 1, 8, 1, 1, negative 1, 0, multiply by 1, 0, no, the other way. 0, 1, 0. This means pick the second column. So that means 1, 8, 1. So that means the eigenvector for lambda equal 5 is 1, 8, 1. This is not unique. This is just one example. Any non-zero multiple is an eigenvector. We can even add sometimes. Okay, so we found eigenvectors. And then you can show that they are linearly independent because where the 0 is. Because you can see in one 0 is in the middle, the other one 0 is in the top. So because of that, you can see that they are linearly independent. So, and then we can add the solution now. So what happens? So therefore the general solution is, so therefore the general solution is x equals c1 v1 e lambda 1 t, c2 v2 e lambda 2 t, plus c3 v3 e lambda 3 t. So if you plug in, you're going to get c1. First eigenvector is 1, 0, 1, E corresponding eigenvalue is -3 plus C2 0 1 -1 times e to the -4t plus C3 181 e to the 5t. So that's the solution, and you can see that Ci are constants as before. They are constants. Okay, so let's just do one last example. So you can see that that's not that difficult. So one last example, again a 3 by 3 matrix. So let's do one with repeated eigenvalues. So repeated eigenvalues. The repeated eigenvalues. So let's say solve. X prime equal, we have 1, -2 and a 2, -2, 1, -2, 2, -2, 1 with x. So this is the system. It's already written in the right form. Again, the first things first, we can find the eigenvectors, eigenvalues. So eigenvalues. So that means the determinant of A minus lambda I, which is equals to, so I'm going to call this matrix is A. So again, we're going to subtract lambda from the diagonal entry. So -2, 2, -2, 1 minus lambda, -2, and 2, -2, 1 minus lambda. If you can use some algebra just to make things easy, so what we can do is we can add the two rows. So I'm going to add row 1 with row 2 because it doesn't change the determinant. It's going to make it simple but doesn't change it. So I'm going to add row 1 to row 2. So if you do that, you're going to get -1 negative lambda, and then -1 negative lambda and a 0. So you add row 1 with row 2. That's how we did. You add row 1 to row 2, row 2 to row 1. That's why I write in row 1. And then also you can add row 3 to row 2 to get a 0 here. So when you do that, you get 1 minus lambda. You get -1 minus lambda again, and you're going to get -1 minus lambda again here, and then you have a 2, -2, and 1 minus lambda. So this is equal to 0. That's what you have. And you can see that the benefit is you can see this term is common, so you can pull it out. See, this is also common. You can pull them out. You can pull those two out. So that's going to make more simpler. So that means so we have so the determinant is, so determinant A minus lambda I equal, so we have so we can expand it from the so you can expand from the first row. If you expand from the first row, before we do that, actually we can pull the -1 negative lambda out. So we have, there are two terms, so we have -1 negative lambda out from the first row and also from the second row. So there are two, and then what we're gonna do is we have 1 1 0 0 1 1, and then we have 2 -1 actually no, -1, it's -2 2 -2 1 minus lambda. Now what we can do, we can expand from the first row. So if you expand from the first row, you're going to get, so I'm going to write somewhere here. So you're going to get minus 1 plus lambda, because you can, because this is square, so the negative sign we can ignore. And then expansion going to be, if you it's one time the minor, which is 1 1 -2 1 minus lambda. That's the first one, and then minus because it's going to go with plus and a minus and a plus, so it is minus. We have 0 1 2 1 minus lambda, and then we can simplify this. So you can see actually it's a square, so you can simplify this. So you can see that there's no negative sign here. So there's no negative sign here. So that's what we have, and then we have 1 plus lambda. We can say this is square. So when you simplify the first one, you're going to get 3 minus lambda. When you simplify the second one, you're going to get plus 2. So that means this is lambda plus 1 squared, 5 minus lambda, which is equal to 0. So this can give you the eigenvalues. So therefore the eigenvalues are lambda equal -1 because there are 2 times, and 5. So there are 2 eigenvalues, one repeat. So what we can do, we can write the corresponding kappa matrices and then see the product. So let's go with kappa minus 1a times kappa 5a. So that means for the first one you want to add a, because the minus 1 means you add 1 to the diagonal entry. So that means you want to get 2, -2, 2, and then you have -2, 2, -2, and then we have 2, -2, and a 2 times the second one. You subtract 5 from the diagonal entry, that means it is -4 and a -2 and a 2, and then this is -2, -4, -2, and then 2, -2 and a -4. Now what we're going to do, we're going to multiply. So we're going to pick a column from this and multiply with a row from that, and you can see when you multiply, you get 2 times -4 is 8, -8, and then -2, -2, +4, 2, 2, +4, that means 0. And you can see that when everything you multiply, you pick a column from the second one, row from the first one, you'll see that everything is 0. So you simply get 0. So this 0 means that, so this is a very special case. The 0 means that these are the eigenvectors of the other matrix. So that means these are the eigenvectors of lambda equal -1. These are the eigenvectors, these columns are the eigenvectors of lambda equal 5. So you don't have to do anything, just pick a column, or you can even scale it. So that means we can write the eigenvectors now. So we can write it. So eigenvector of lambda equal 5 are simply V1. Just pick a column from the first matrix, even scale. So what I'm going to do, I'm going to pick the first column and divide by 2 just to make it simple. So that means it is 1, -1, 1. So that's the eigenvector for lambda equal 5. And for the second one, we can do the same thing, but you need 2 eigenvectors. That means just pick 2 columns. Just pick 2 columns, or even after scaling. So so that means so we can have, so I'm going to write here eigenvectors of lambda equal -1. So you can say just pick one column. So it is V2. So let's pick the first column, and also you can, actually I'm going to pick the second column and divide by -2. So you pick the second column and divide by -2, so you're going to get 1, 2, 1. And also we can pick the second column, the third column, and divide it by 2. If you do that, you're going to get 1, -1, -2. So there are other options as well. You can even add 2. So let's say if you add these 2, what will happen? If you add them, you're going to get 0, -6, -6. That means you can have, because you get 0, -6, -6. If you divide by -6, you can have an eigenvector 0, 1, 1. Also, if you add the first 2, you're going to get -6, -6, 0. if you divide by -6, you can have eigenvector 1, 1, 0. So those are other options. So you just pick any two. So it doesn't matter. Either you pick the original column or scale version. So it doesn't matter which one you pick. Just pick something that is easy to work with. So that's it. So we find all the eigenvectors. Now we just need to write the solution. So the solution is, so we can say, and then also they are linearly independent. So they are linearly independent. They are linearly independent. So thus, the general solution is x equal c1 v1 is the eigenvector e lambda 1t plus c2 v2 e lambda 2t plus c3 v3 e lambda 3t. So this is equals to c1 times the first eigenvector is 1, negative 1, 1, e to the corresponding eigenvalue 5t plus c2, we pick the eigenvalue vector as 1, 2, 1, e to the negative t plus c3, we pick the eigenvector as 1, negative 1, negative 2, e negative t, where c1, c2 and c3 are constants. Okay, so that's it. So you can see that that's not that difficult. So the only thing that you have to do is find the eigenvalues first and then find the corresponding eigenvectors, and we just plug in there and get the solution. Okay, so that's it. So thank you.